Sure. So just want to make sure everybody can see my screen right and hear me okay.
Yeah, all good.
Okay, cool. So as Alexei have already said, today we're going to be talking about this fundamental paper called Impossibility of Distributed Consensus with One Faulty Process. And before we get into the paper, just a little bit about myself. I'm a third-year PhD student from MIT's Data Systems group. That is, I basically work on databases, supposedly, but I actually mostly work on distributed systems. Specifically, I work on new fault tolerance guarantees in the cloud. But we're not here to talk about me. We're here to talk about this paper. And before I get into that, just want to acknowledge that thanks to Professor Nancy Lynch from MIT, she has allowed me to use a lot of her slides and a lot of her materials. You can find her book here on the right, and the course that she teaches on distributed algorithms. I think this is actually available for MIT OpenCourseWare if any of you are interested. Anyway, let's get into the topic of consensus. So I think for this particular group, I don't really need to convince anyone that this is a fundamental problem in distributed systems, right? So the typical use cases include, obviously, if you want to commit a distributed transaction, if you want to do any sort of leader election, resource allocation, or even in non-traditional cases, for example, if you've ever flown on a plane, the distributed consensus is there to keep you safe, to have all the sensors agree with each other, even if one of them is faulty. Right. So really, for such an important problem, this is a surprising result of impossibility that's being presented in this paper. The natural question people would ask, like first-time learners of the distributed system would ask, is really, what's the point, right? Should we really all just go home because there's an impossibility result? The point of this talk is to convince you that the answer is yes and no, right? So we still have something to work on, although there are certain things we should really just not try. So without any more fluff, let's get into today's talk. So I think for this presentation, I want to actually go a little bit heavier on the background and setup, and also on the part that puts FLP in context. I think the proof itself in the paper is pretty dense, although it's well written. So I guess we will have a brief section where we talk mostly about the intuition and the sort of, at least the problems I had when I first learned the material, as opposed to sort of going straight across the proof line by line. That sound good? Cool. Let's first talk about the background, right? Let's dial the time back to, 1980, just say 1980, right? So this paper was actually, FLP paper was actually first published in 1983. I know the paper itself says 1985, but actually it was published in PAWS before that. Back then, what do we actually know, right? So even back then, people are still very interested in distributed systems, not necessarily in the context of machines talking to each other on the internet, but also in the context of just processors talking to each other within a single machine, right? So naturally, the sort of more theoretical part of the systems community came up with this abstract concept of consensus, which hopefully makes it a lot easier to actually sort of cuts down a lot of the complexity involved, obviously, in building real systems. So let's think informally of what consensus means, right? A group of machines, really, or processors, need to agree on a value by communicating with each other, right? So everybody only has access to local information, although you probably can assume that everybody knows there exists a set of other people in the system that you need to talk to. It sounds like an easy problem, but obviously there are lots of complications in this simplified model. You can have failures of processors and the links, and you can have uncertainty due to asynchrony of said channels. We'll get into each of those in detail. But depending on the actual setting you choose, there are different bounds or impossibility results for distributed consensus. Just to give you a couple, you can have a synchronous setting, asynchronous network, shared memory, partially synchronous setting with different types of failures. And even before this paper was written, a lot of results already exist in sort of the field of consensus, right? I'm just actually going to present two key results that hopefully will set up this result pretty nicely, as they also actually share the same model for the systems. So the two results we're going to talk about is, one strong impossibility result, which is the two generals impossibility. One really promising result, which I think was discussed on Slack earlier as well, which is synchronous consensus in the face of processor failures. And the hope is that understanding these complementary results really help put FLP's assumptions and significance in context. first to talk about link failures, right? This is also known as the two generals problem. This is first proved impossible by Jim Gray himself in 1978. The sort of colloquial informal statement of the problem goes that there are two generals or more who are planning to coordinate an attack. For them to succeed, right, all of them actually have to agree on whether to or not to attack. Obviously, them being generals, they would prefer to attack if possible, right? Each general sort of has an opinion to start with of whether their troops were ready, whether this is a good idea to sort of attack, but they have to exchange opinion through unreliable messengers. And these messengers sort of go through enemy territory, they can get captured or lost. But let's be generous about the messengers and say, like, we know an upper bound for them to arrive if they are successful, right? So this is actually sort of a synchronous setting, if you will. Enough with the stories, though. Let's try to formalize this a bit more, right? Assume a system model where you have a connected undirected graph, like the one you see on the right. Here, every vertex is sort of a processor, and every edge, well, double sort of sided edge, is going to be the communication channel, right? We're assuming a synchronous model where basically you can have rounds of communication going through and say, if a messenger hasn't arrived in a day, we know the messenger has been lost, and we can sort of move to the next round. And everybody sort of agrees on how long a day really is, right? So that's the synchronous model. Each process in this graph has an initial value of 1 or 0, representing whether the general agrees to attack or not, right? And in this particular example, any number of messages can be lost on these edges, right? All processes must output either 1 or 0. So you can think of it as setting a special output variable in a function or actual physical processor. And changing the output is not allowed once this has been written. So sort of a one-shot thing, you get one shot to get the decision right. And let's talk about correctness condition in sort of formal terms, right? There are really 3 important correctness conditions we want out of a good algorithm. One is agreement, right? So this is consensus after all. So we want in any trace, no 2 processes should decide differently. And because sort of decision is a one-shot thing, that also means anywhere throughout the entire decision process, no 2 processes decide differently. So that's sort of the fundamental requirement of consensus. The remaining 2 are really there to sort of guard against bad scenarios, right? So one of them is validity. The way to think of validity is there are obviously different definitions of validity depending on the assumption you choose. But the key point is this, right? So imagine a trivial algorithm where everybody always says 1, where everybody always says 0. That obviously solves consensus. And to sort of guard against this kind of stupid solutions, if you will, we introduce the validity condition, which says at least you have to try to do something, right? So if one of them starts with, if all of them start with 0, you must output 0 or something like that. So, and this is actually pretty important for later proofs as well. But for now, let's just leave it at that. And the third sort of condition is termination, right? So obviously we want our algorithms to terminate. So for any realistic algorithm, we want processes to eventually decide on the value. Any questions so far? Nope. Okay, let's move on. So because we're mostly talking about the FLP proof, we won't get into details of this proof. But as some of you might already know, this is impossible, right? So surprisingly, you cannot even achieve consensus for the simplest case, which is 2 generals on the right here. And Jim Gray proved it with a sort of also a contradiction method. We can briefly sketch that here. You can assume that an algorithm sort of solves this and it accomplishes that within our rounds of communications, right? You can show that if you start removing messages to one of the process, right, the other process obviously didn't notice any different because they received all the same message as they did in the previous successful execution. So that process has to still decide on the same outcome, which would force, by agreement, the earlier process to decide on the same thing. And you can sort of keep doing this trick of removing messages until the 2 processes don't actually communicate with each other at all, and they still reach the same result. At that point, you just flip their input value and be like, oh, you can't possibly decide on something different because you're a deterministic algorithm. And that would lead you to a contradiction that shows this is not actually possible, right? Now the question is this really a bad result? Well, first of all, obviously there's the theorem that no algorithm exists to solve the coordinated attack problem for even a 2-node graph that obviously generalizes to arbitrary graphs. But it's a sad result. It still makes sense, right? So the intuition behind this is imagine a trace where in this model, there's zero connectivity with every message sent across the link lost. Obviously, they can't possibly do consensus on anything, right? So that's fine. Somewhat sad, but still understandable. Now let's talk about the good news, right? We just proved that link failure is really not something you can solve in this particular setting. Let's talk about process failures, right? So consider process failures. You can be stopping or Byzantine. Both turned out to be solvable with asynchronous network, but let's focus on stopping, right? We have the same agreement problem for stopping failures as before, except we basically have to worry about what happens with failed processes. Let's arbitrarily assume that up to F processes may fail in any situation. And the termination condition basically changed to only apply to non-faulty processes. If a process dies, well, it does whatever it does. But note that very strongly, agreement and validity remains the same, right? So even if a process fails, that doesn't mean it gets to decide on a different value than the rest of the cluster, right? If the process decides before it fails, we have to stick by that agreement. That's at least for stopping failures. So what do I mean by stopping failures? Well, processes can stop at any time, in the middle of a round, before a round, or after a round. That said, we get to assume that the messages they send are actually atomic. Either a message is sent entirely or not sent at all, right? But that doesn't mean all of the messages are necessarily sent that the process wanted to send, right? So you can look at this sort of animation over here, say this process is dead. What that means is if it wanted to send 4 messages, maybe only 3 of them got delivered, right? And the dead process sort of stays dead and will not perform any further actions. This is in stark contrast to what we call a Byzantine model, where failed process can do whatever it wants, right? And another important thing to get out of the way is that a dead process, usually in consensus, does not impact connectivity of the graph, right? So that means there are some weird graphs where sort of a center node dies and the graph suddenly is no longer connected. That won't be the case for any of the things we talked about here. Let's just assume an n node complete graph for simplicity of the problem. Okay, so this turns out to be a solvable problem in synchronous network. And this result was presented by Fisher and Lynch in '82, which is the F and L in the FLP paper, if you notice. So this result is actually going to carry a lot of the same model we're going to talk about later, which is why I think this is super useful. They also proved in the same paper, which is actually the main result of that paper, there's a lower bound of F+1 rounds to tolerate F failures. This is not really relevant detail for this work, but hopefully it should make intuitive sense what is true from the algorithm we're going to present. The idea here is pretty simple, right? If you are a processor in this synchronous network model, what you do is basically you keep sending all the values in the cluster known to you to the rest of the graph. And eventually, like everybody will know the same thing, and you'll use a simple decision rule to make a local decision. Say, I know of 10 people's value in the cluster, 6 of them are ones, 4 of them are zeros. The simple decision rule could just be a majority vote, in which case you say, oh, there are 6 ones, let's output 1. So everybody obviously can do that by themselves once they have a view of the cluster. More specifically, let's do sort of a bit more formalism in this. Each process stores a mapping of some known subset of W, that is with regards to the rest of the cluster. Basically say there are 10 processors, W is going to be sort of a set of 1 to 10. And you map the cluster nodes to their initial value of zeros or ones. And the algorithm is going to repeatedly broadcast W and add received values to W, right? You begin with only knowing your own value. Now you tell everybody else about your own value and hear about everyone else, and you sort of construct a view of the cluster that way. And this algorithm can stop after the first failure-free round, which is guaranteed to happen, obviously, after F+1 rounds, because we only have F failures. In F+1 rounds, at least one of them doesn't have any failures, sort of pigeonhole principle, right? Well, reverse pigeonhole principle, but anyway. The intuition behind this algorithm is pretty simple, right? If there is no failure, then on the first round, everybody would know about everybody else's value because all the broadcasts succeeded, right? You can decide directly with no issue. That's fine. The only complication is that a failed process, as we talked about earlier, actually can send only its value to a subset of its peers, right? Which means if a processor failed in a round, there's going to be a split brain situation going on in the cluster, right? So some of the nodes who receive the message from the faulty process is going to say, oh, I know of this additional value, whereas the other nodes don't, right? So that's going to be a problem if they, at that point, make a local decision, they could perceivably arrive at a different decision. So that's bad, which is why if you have a failure round, everybody would just have to keep talking to each other. And the first failure-free round, everybody would agree on what the cluster state looks like. And that is when you can actually decide, right? And obviously slow down, let me know. Let me slow down and tell me if you have any questions. But hopefully it's pretty clear that this algorithm solves the problem, and you can use any arbitrary decision rule at the end, and everybody would agree on a value despite failures. Okay, so some bad news, some good news, but the synchronous result seems pretty strong, right? So far it seems pretty clear cut. Consensus possible with processor failures, but not with link failures. And this is a result we take advantage of every day. If you ever fly in a plane, as we saw, this is probably the algorithm they use on the actual planes themselves, obviously the Byzantine version. But the problem really here is, so far, we've only assumed the synchronous model of communication, which forces, as we said before, every process to step together, right? So this is a reasonable assumption for many cases. For example, if you have 10 processors hooked up to a single motherboard or share a clock on a sort of a single chip, obviously reasonable for them to step at the same speed, and that won't be much of a problem. But there's a very limiting assumption if the two processes you talked about are data centers on the opposite side of the globe, right? That's a huge hundreds of millisecond delay. It's not reasonable for them to sort of coordinate that. So this is where the topic of asynchrony pops up in consensus, right? A lot of the times, if you are sort of well-versed in the formal literature around synchronous networks, the proof method of choice there is induction on the number of rounds, right? So it's pretty clear that everybody starts out at some initial state, they agree on going to the next round, some messages got sent. The natural thing to do is to do induction on those rounds. But in an asynchronous network, there are no timing assumptions, which means one processor can take 10 steps, whereas the other processor only took one, or maybe a message is arbitrarily delayed, and you can't assume anything of this timing, which removes the construct that's essential to so many proofs in the earlier results in this field. And obviously asynchrony sort of applies to not just network, but also shared memory. Those turn out to be largely equivalent, but let's not get into too much of that in this talk. So here's what an asynchronous network might actually look like. And this is actually what the model they use in the paper, although not explicitly said. You have the same processors, right, in this sort of P1 and P2, the blue circles in this graph, that works very much the same way as before. Obviously, there's sort of, they can take steps at their own pace, but that's largely fine. The biggest problem is with these additional channels, right? So you have channels of communication in addition to processes, and they are modeled as processors actually in a lot of formal theory surrounding asynchronous network. So what do I mean by that? By formal, I mean that a lot of the work underlying this asynchronous network uses what we call an IO automata model. So processors and channels are actually both automata in this whole model. What an automata does, obviously, it can receive some input, it can send some output, it can step its internal state. The details are not really relevant for this talk, although the FLP proof is built on top of obviously a lot of work in this area. The proof itself can be written without sort of any of this formalism, but the usual suspect sort of applies in this model, right? You can have automata being defined as a 5-tuple of some symbol, some state set, some transition function. Transition function has to be deterministic, but timing of the stepping doesn't necessarily have to be, right? Okay, the only automata we care about for this particular proof is actually the channel automata, right? So that is the, you can think of that as sort of your network router in a real data center, or sort of the abstract channel or of communication between two processes, right? Their semantic is pretty simple. You can send a message to a channel automata, right? That'll enqueue it onto some internal FIFO queue, which is ordered. So think of that as a receive an action, it sort of changes its internal state to include that in its queue. And at some unspecified future date, it's going to emit that result into the the downstream consumer with a receive symbol, right? So send is the input, receive is the output. It maintains an internal state of a FIFO queue. And additionally, it sort of guarantees that all the sends are eventually received, right? So it kind of operates as a reliable messaging channel, but the catch being that, well, it's perfectly allowed for the China automaton to sit on your message for arbitrarily long, as long as it eventually sort of delivers it, right? So if you think an automata is not going to deliver anything beyond 30 minutes, well, it can go for a coffee and deliver it at the 31st minute. That is perfectly allowed. Okay, so hopefully we've explained asynchronous network model a bit more. And let's actually focus on the topic of today's talk, which is consensus in asynchronous network, right? And it's largely the same problem. It actually has almost exactly the same setup as the synchronous version we talked about earlier, that is Fisher and Lynch's 82nd result. And the only difference is that we're replacing the network model on the top side, so this sort of star shape, into the asynchronous model on the lower part of this slide, right? So fail stop as before, no link failures. Obviously, the formal problem statement is going to be slightly different due to IO automata, but they didn't consider that in the paper, and we don't have to talk about that as much as well. As you probably already know, this turns out to be an impossible result, right? And this is proved by Fisher, Lynch, and Patterson in 83. Other equivalent results and alternative proofs sort of exist, but let's focus on this one. And this turns out to be a very fundamental result. Okay, so that is the background part of this talk. And before we move into the proof itself, anybody have any questions or discussion or concerns? Nope.
I think all good. Yeah.
Cool. So let's jump into the proof itself, right? Let's read through the theorem they're claiming and in the paper, right? In an asynchronous distributed system in which at most one process may stop without warning, it is impossible for the non-faulty processes to reach agreement reliably. This is a very, very strong result, by the way, right? And seems very counterintuitive, because what this says is if you have a network of arbitrarily large processors, right? You have 10,000 processors. If one of them fails, the remaining 9,000 something processes don't agree on a value, which seems overly strong, right? If one process dies, why would the other processes fail to agree? And as a fail stop sort of process model we're assuming, like intuitively what you should be able to do is you should wait long enough to see, oh, that guy's dead. And then we just like agree amongst ourselves, like let's exclude the dead person and let's just run the algorithm as if we're failure free, right? Because we only have one failure. And even if you tell that to the rest of the system, they still can't do that, right? This is a very strong result. So let's actually, to sort of grasp the significance of that result, let's actually go through the proof itself, right? The original FLP proof, as you know, is actually by contradiction. And there are some earlier discussion on Slack that says, well, yeah, this can be rewritten into a constructive proof, which makes it machine checkable. And that is very nice and very cool, but we're actually not going to talk about that too much in this talk because the proof is very much the restatement of the things we're going to do here. So let's assume, again, for the proof, there's that you have a one fault tolerant asynchronous algorithm that solves consensus in the setting, and we want to reach a contradiction based on the requirements of the algorithm, right? So let's restate those requirements here. They are very, very much similar to the ones we've seen before. You have three key properties you have to have, which is validity. We're using the weakest form possible actually in this case, which is if all of them start with ones or zeros, they better all agree on ones or zeros, right? You have termination, which is also the weakest form imaginable, really, we're using in this result, which is some non-faulty process eventually decides, right? So doesn't have to be all of them, just one of them has to decide. And you can actually sort of simply see why that would be the case, right? Because if one of them decides, they can enter a special state and broadcast a special message to everybody else and says, please decide, I've decided, right? So it's sort of the same as strong termination, but it turns out weak termination is sufficient for this particular proof. And the final thing we sort of keeping without change, which is agreement, no two processes, dead or alive, decide on different values. You can be undecided, but you cannot decide on a different value. And the contradiction we're going to be deriving actually takes advantage of the termination weak statement. We're going to basically assume the rest and prove that you cannot have termination. Okay, so before we get into any more stuff, let's get rid of the terminology along the way, right? So a configuration of the system is defined as the initial input to all these processes plus the channel automata state, right? So what's in the message queue everywhere in the system. Noticeably absent from this is the processors themselves, right? And the reason for that is pretty simple. We can't possibly care about the processors if this proof is to work for any algorithm, right? So they can have any state they want. We can't assume anything of them. A step in this system is going to be anything that takes the system from one configuration to the other. So you can queue a message, you can step the processor, and then you can enqueue some more messages. So because the internal transition of P is really deterministic in automata theory, the only thing that really matters is the initially dequeued message, which will define the entire step, right? So let's call that an event, which is to dequeue a message from somewhere in the channel automatas into a recipient. So E equals M and P, that is the tuple of message and processor. So this will deterministically trigger a step. Although very importantly to notice that because we're working with an asynchronous network, the message here doesn't have to be an actual message, right? It can be the absence of a message. So M could be sort of a special empty message to just make sure that every processor can just always do a local step. Okay, so last but not least, let's talk about schedule. Schedule is basically a sequence of events that can be applied to some configuration and sort of an in sequence, right? So, and this sort of from schedule, we have the notion of reachability or messability, right? So if you can reach another configuration from one configuration with a schedule, that means the C prime in this case is actually reachable from C, right? That's just one terminology that's good enough. Okay, so if you're like me, when you're reading this, you probably have a lot of questions, right? So two things I want to sort of highlight in this setup, right? First of all, no concurrency anywhere in this setup, even though, like, obviously in the distributed system, lots of things are happening simultaneously all the time, right? But here's the interesting thing, right? Because every process deals sort of steps locally, if steps are concurrent, they do not interfere with each other. So in the paper, they actually have some formalism around this. Basically, lemma 1 is the proof that concurrent messages are really commutative to this whole sort of scheme, and you can reorder them in the sequential version of an algorithm execution and get the same result. So it's sort of helpful for us to just think of sequential traces then, because it's the same thing. My head just wouldn't explode if I'm thinking about things happening in sequence. In general, if we can prove impossibility for the easier sequential case, this sort of extends, obviously, to the harder concurrent cases. Like if you can't solve the sequential case, how can you possibly hope to solve the concurrent case, right? So that'll be a theme we take throughout this presentation, is that for impossibility proofs, right, weak guarantees, strong assumptions are always good because that's a stronger impossibility result. Basically, the same goes with this atomic step, right? So in the setup we said earlier, an atomic step of the system actually consists of receive a message, step some internal state, and broadcast a set of message, arbitrarily many, to the rest of the system. This is a lot of stuff, and normal systems cannot guarantee that in one atomic step, right? We're actually assuming that in this proof, and as we said, this is fine because if you can't solve it with a stronger primitive, there's no hope for you to solve it with a weaker primitive. And this actually simplifies reasoning for the proof by a lot because we don't have to think about partial delivery or anything like that. And it yields the same result. So let's just do that. Okay, one final bit of terminology before we get into the meat of the proof is the problem of valence, right? If you read the paper, you know throughout the paper there are some terms thrown around, which is bivalent, univalent, all these things. That's really a fancy word for a very simple idea. If you have from an accessible configuration, if all reachable configurations have decision value V, we just call the configuration univalent, or specifically, like if it's all zeros or all ones, let's just say 0 valent or 1 valent. Otherwise, the configuration is bivalent, right? If no reachable configuration has a decision value, that obviously is not allowed because then the thing won't terminate. So every configuration is either univalent or bivalent, right? Basically, when I say something is univalent, the system has decided at that point of the execution, right? Everything that happens from there has to reach the same decision value. So the system has decided by that point. So to draw some example to draw your, let's sort of like using a familiar example, say in Paxos or like two-phase commit, right? So in two-phase commit, if the sort of everybody has written down an accept to their disk, you can say, oh, this is the point where the system has decided this is going to commit, right? See something in the chat. Atomic step, easy or weak assumption. So this is actually somewhat of a weird discussion because sort of depending on your viewpoint, you can either say something is weak or strong, but by strong, I usually mean like you have a strictly more powerful primitive that I'm sort of able to write simpler programs, if you will, with a atomic broadcast primitive compared to if I have to sort of manually, like if I only able to deliver a message atomically, right? That's strictly less I can do in one instruction of the system. Obviously, that's not a formal definition, but that hopefully that helps understanding, right? Okay, cool. Any other questions before we move on to the lemmas? No? Cool. Okay, so the way we're going to cover this proof, we're not going to go by the papers themselves. So I'm actually going to repurpose one of Nancy's talk from 2020, where we talk about the intuition behind the proof. So the claim is this, right? The center of the proof, the heart of the proof, is actually just this diagram on the right here. This is the goal we want to achieve in the proof. If you have a good algorithm, we will be able to find this pattern in a schedule somewhere, right? So let's unpack this a little bit. Can people see my cursor?
Yes.
Okay. So let's say we have C0, right? And from C0, we can actually reach two different decisions, one 0 and one of 1. Obviously, without loss of generality, if we want to flip those around, that's fine. The interesting thing here is this, right? So the same message got delivered, which resulted in the decision being made. The only thing that's different is the timing. If I take another step, or equivalent several steps, we'll talk about that later, it results in a different decision for the system. Why is this important, right? Think about it. If you can think of the execution of an algorithm of us just walking on this sort of graph of connected configurations, right? And you're deciding as an evil person who's trying to make the algorithm not terminate, which fork to take if you're at C0, right? Like basically, if you are the evil person, you are the adversary of the algorithm, you get to pick which message to deliver at what point to make sure the system doesn't terminate. If you're that person, and I tell you that nowhere in the system does this pattern exist, right? You can always just pick the fork that doesn't terminate, right? So this pattern forces someone, basically, this pattern tells the adversary that no matter what message you send, if you're at C0, I'm going to terminate. And that has to happen somewhere, because otherwise the adversary just loops around and like always pick the bivalent path. And that's not good, right? So what we have here is this, right? We have to find this configuration somewhere in the algorithm execution. And the decision here really hinges on the timing of this particular message, PI and N, right? Okay, so that probably would be very confusing for many people, which is why I think it's a good idea to unpack some of the ideas behind this graph, right? So why this specific pattern? From earlier discussion, we've sort of shown that for any algorithm to terminate, we must exist one message that is a tipping point somewhere in the decision process, right? And because M prime here can always be the empty message, it doesn't really need to depend on other messages, right? So like there won't be a situation where we can't find this pattern because there aren't enough messages in the buffers, one. And two, you can always take a schedule and reorder it with lemma 1 until we get exactly this pattern where the decisions are adjacent. So this is somewhat of an involved process to show, which is why I'm just going to ask you to sort of take my word for it. But basically, because message channels are fivefold, if I delay PIN, right, like I don't allow this channel to emit a message, well, eventually I'll run out of stuff to do that's sort of independent. First of all, everything happening elsewhere in the system are concurrent with this message, right? Because there's no dependency between this message being delivered and all the other messages that are concurrent with it. So I get to play around reordering them however I want. And eventually I'll run out of stuff to do. So I have to deliver this message. Otherwise, I'm basically sort of stuck, right? So you just have to take my word for it that this pattern is a fundamental pattern. And if you don't get this in a particular execution, you can always reorder it so you get this configuration. Okay, then let's go back to the paper. Surrounding this pattern, right? So lemma 2 basically shows that we can find a bivalent C0. Like we basically start off being undecided, which will lead us, like there definitely is possible for us to get a configuration like this somewhere in the algorithm, right? This forces D1 and D0 to actually have different valence, which is important. That's where we're going to derive a contradiction later on. And if you are very familiar with the paper or you're a very astute sort of observer, you might notice that the existence of this pattern is actually the opposite of lemma 3, right? So if I can show that this pattern doesn't exist anywhere in the system, I basically have lemma 3. And that is what we're going to do actually here, right? We're going to proceed with a contradiction to show that this pattern cannot exist. Hopefully everybody's on board with that plan, and let's just go into a relatively short proof actually. Split into two cases, right? So one, I and J is not the same processor. Let's try to see why this doesn't make any sense. So let's deliver sort of the same message here, right? The message that resulted us from going C0 to C1 to D0. This is obviously allowed because they are concurrent, as you can see here. And wait, these two steps are actually sort of by lemma 1 interchangeable with each other, right? So like there shouldn't be any difference if I send this first versus that first, because they happen on two different processors. Two processors that didn't communicate with each other, by the way, right? So it can't possibly result in one being 0 and one being 1. So that's a contradiction, right? Sort of violates local processing, if you will. The second case is slightly more involved, but let's say I and J are actually the same processor, right? We can't use the algorithm from before, but what we can do is this. We get one failure, right, in the setup, like we are allowed to fail one process. Let's just fail this particular process and see what happens, right? Say PI actually failed in C0 over here. Messages still can be delivered, just simply that PI won't do anything about it because it's dead, right? It won't send any future messages, which is why this is actually going to be a problem, because the rest of the processes do not get to know which path the system took. Because the only way they can find out about it is by hearing about it from the failed process, who is dead, right? So for the rest of the system, there's no way for us to actually determine which path was taken, which is another contradiction, right? Because then the rest of the system also reached two different decisions based on which path is taken. So that is also not possible. And we have reached a contradiction on both cases, which tells us this pattern cannot possibly exist anywhere in an execution of an algorithm. Okay, so hopefully that's the key lemma, and I've managed to convince most of you that this is correct. And let's just wrap up based on that key lemma, right? So we've shown that this pattern on the right here does not exist anywhere in the system. Or equivalently, we have lemma 3 from the paper. Then it's the same logic we applied before, right? If you are an adversary and you're executing the algorithm, you're controlling the execution of the algorithm by picking which fork to go at every configuration, you just pick the one that doesn't make a decision. And you're guaranteed to always have one such fork available to you, because otherwise you will have this pattern, right? And that obviously contradicts termination, and that'll tell us that consensus is not possible in the asynchronous setting of the network. Okay, so let's summarize it in plain English. Basically, no math involved in any of this reasoning. Lemma 1 says that concurrency does not matter in this setup. Lemma 2 says processes must initially be undecided on the outcome. Lemma 3 says there exists a way for processes to remain undecided because of a delay of some message, right? And putting it together, what this says is processes can remain forever undecided. And that is the result. Any questions on the proof? No? Okay. And hopefully people have sort of recovered from the shock that this is not possible, even though this is the 40-year-old spoiler. So let's try to unpack this a little bit, right? Exactly what went wrong in our formulation of the asynchronous version of the problem that turn a solvable thing in synchronous setting into an unsolvable thing, right? In fact, we assumed even more in the asynchronous version of the network, right? It cannot be that their impossibility result cannot stem from any of the other decisions we've made. Like we have stronger primitives, we have weaker guarantees, right? In fact, if we were to just assume the things we did for the FLP proof, take it back into the synchronous setting, algorithm is trivial, right? Like we have atomic broadcast, just one round, everybody decides. It's like magic, right? But we cannot do that because asynchrony is actually a fundamental thing for the impossibility result. Particularly if you think about it, processes cannot tell if a late message means someone is dead or just slow, right? And the whole thing Lemma 3 is trying to tell you is that you must avoid making decision based on the absence of a message, right? Because if you do that, well, like chances are you're wrong because the rest of the system maybe got that, maybe got some information and will go to a different decision and you'll be stuck with your wrong choice, right? And that is sort of fundamental to asynchronous model because messages can be arbitrarily delayed. You have to make a decision based on the absence of a message, which is unsafe, right? Okay, so wait up. All of our modern networking infrastructure is asynchronous, and for good reasons too, right? You cannot make synchronous networks performant for most of the cases that we have these days. Now, FLP's networking model is actually much stronger than TCP, right? Again, we have atomic broadcast, we have like all these nice guarantees like strict FIFO, like not even have to do any sort of retry or congestion control. Why are we still here trying to solve consensus? We can't do it for like a super strong networking model. Let's just all go home. Like this is hopeless, right? Obviously, that's not the case. Consensus is actually too important of a problem in real world for us to stay depressed and just not attempt a problem, right? For example, my entire discipline, which is distributed transactions, wouldn't even exist if we were to stop working on consensus because of FLP, right? Distributed commit is, if you will, strictly harder, if you will, than consensus. And we have to do that in a distributed asynchronous setting for any realistic data center applications. So this tells us FLP, like many other impossibility results, sort of simply puts limitations on the kind of algorithms one can look for, as opposed to just tell you don't look for any algorithms, right? As usual, we actually have two options here. We can either strengthen the assumptions of our system model to make this possible, or we can weaken the guarantees and make this possible, right? Let's look at each one of these options. So first of all, we can try to relax the assumptions, right? So assumptions here are fully asynchronous network, deterministic transition, not much else there, right? This is a pretty strong result. But fully asynchronous network really rarely exists in practice, right? Like you don't have an evil person deciding which message to delay in your network. Like it's going to be bound by some real world constraints like distance, congestion, or something like that. And as for deterministic transition, computers can be said to play dice. So we don't have to actually abide by sort of determinism. Still, most practical work do not try attacking consensus from this angle. What I want to call your attention to is actually to attack the guarantee, right? Of the three guarantees, agreement obviously has to remain, like this, the core of consensus, right? Validity also must remain, right? Because if you're just going to go around doing trivial solutions, that doesn't help anyone. So the only thing we can attack is actually termination. Incidentally, this is also the thing we derive the contradiction on in FLP proof. So if you have something that might not terminate, the proof doesn't break your algorithm, which is super nice. Okay, so not going to go into too much about assumptions. Here are a bunch of pointers in work in this area. You can sort of check it out offline. I'll send the slides to the Slack channel. Let's focus on the guarantees, right? Basically, termination only need to apply in certain situations, practically or theoretically, right? Typically, if you have a sufficiently long period of failure-free execution and reasonable execution timings, that is, the processor doesn't sort of take forever to execute one instruction, you can actually solve this problem. The FLP paper itself already hints at this with its section 4, which is initially dead processes. So this sort of is equivalent to the assumption that there's a failure-free execution period where everybody can actually decide, right? So well-known consensus algorithms are almost all developed along this line. This include view stamp replication, which this reading group covered before, Paxos, Raft, and a bunch of work from the theoretical community that very much similar to all these. Cool, and that's all for what I had to say today. And let's open up the floor for discussion.